A2 Further Maths, Coupled Differential Equations. Alright, so we'll just have a look at trying to find a general solution for x and y in terms of t. Now the problem is, if I look at just a single equation on its own, you'll notice that we've got three variables there. We've got x, we've got t, and we've got y. So on its own, you can't really do that much with it to try to solve it. You can't do it. Even if you tried to integrate in terms of t, then you've got some integration of y going on here. So we can't really do anything with it. But we haven't just got one equation, we have two equations. And because we've got a second equation that links y, t and x, we can have a go at solving those two equations simultaneously. Now we've seen something like this in your normal maths with parametric equations. And what we do is we write one equation in terms of maybe t, x or y, and we can substitute in the other. And there's no difference in this one. What we can certainly do is we can say we know what y is here, for example, d over dt y equals 9x, we could just substitute that in. But another way of thinking about it, a technique that's worth doing, is just seeing if you can just differentiate this equation just here in terms of t. So if we differentiate that equation in terms of t, what we're going to end up with is d squared x over dt squared equals dy over dt. Now the reason why that's helpful, of course, is that dy over dt is given to us there. So really, we can replace the dy over dt for 9x. So therefore, we end up with this equation. And you'll notice that we've managed to cancel out our y values. So because we've managed to cancel out our y values, we can now solve this second order derivative. And you can solve it just by finding the two solutions. You can see we're going to get, in this case, if we rearrange it and write the auxiliary equation, we got two solutions, which is going to be plus and minus 3. So we got plus 3, we got the minus 3, and there's our solution to our differential equation just there. And that's the solution they wanted. They wanted x in terms of t, x in terms of t. How could you work out the y value? Well, you could substitute it back in, the same as you would do earlier on. Or sorry, normally. Now, if you look at this situation, trying to put it into this equation means I need to differentiate it first, and that would tell me what y equals. If I substitute it into this equation, I could substitute it in straight away, but then I'm going to have to do some sort of integration to get y. So it's probably easier to think, right, if I differentiate it, that's going to tell me what y equals straight away. So I'm going to substitute it back into here after I've differentiated it, and I get y equaling 3a e to the 3t minus 3b e to the minus 3t. Okay, so well done if you followed that. Okay, can you just grab your notebooks then? What we're going to do is just going to formalise this a little bit. So I've got a pair of first order simultaneous equations. So a pair of first order simultaneous equations. And you'll notice that it's got the three variables that we talked about earlier. We've got an x, we've got a t, we've also got a y in there, and we've got some function of t. That's what it's saying there. So you can have something to do with t. But the key to these differential equations you're dealing with here is making sure that you don't have anything more complicated than just an ax plus by. So anything more complicated is beyond the course. You'll deal with those later on. So for now, as long as you've got this sort of situation where we've got just as first order derivative equals some amount of x plus some amount of y plus whatever function of t you like. It might be sine t, e to the 3t, something. Okay, just t squared. It doesn't matter. Same with the other function. The differentiation of y in terms of t must equal some amount of x plus some amount of y plus some function of t. Okay, and just to remind you, as you can see on here, t is the independent variable. That's always the number that's on the denominator part. What's it in terms of? That's your independent variable, whereas x and y are dependent variables. Okay, so we're going to solve it by taking that first derivative just there. Okay, and what I can do is I can differentiate that. Now if I differentiate it, I'm going to get, as you know, in terms of t, I'm going to get d squared x over dt, go through dx over dt, dy over dt, plus some function of t being differentiated, hence the dash. It doesn't matter what they choose. Like I said, that could be sine x, then that would be cos x, and so on. Okay, so whatever the function is of t, you just differentiate it. Why does that help you? Well, you know what dy over dx is. So if I start working with that, I can substitute both the y value and dy over dt back into this second function. So rather than trying to substitute that into there, what you're doing is you're just using this function, you're getting the y value and you're getting the dy over dt value, and you could substitute them in. So if we do that, then we can solve the second order derivative to find the solution. So once we've substituted both of those into there, we can then find the solution. We can't do it with these, of course, because they're just too complicated, but that's the important steps. Differentiate one of the equations, that will give you both variables for y and dy over dt, and substitute that into the second equation. So just pause there, take down what you need, and move on to an example. Okay, so sticking with your notebooks then, just getting this example down for your notebooks, and feel free to have a go at it first. If not, we'll work on it together. So just pause there, get down what you need. Okay, so we'll have a look at this together. So the first thing we need to do is just find the equation. Doesn't matter which one you pick. All right, pick any one you like. You can take this equation just here, and can you work out what y equals by rearranging it? And can you work out what dy over dt equals? Then if you know what both y and d over dt is, then you can substitute them in here, and then you've got an equation with just x's and t's. So what's y then? Well, we're not asking for like the full general solution for y, we can do it in terms of dx and dt. So we're going to rearrange this, and we know that y equals dx over dt minus the 2x minus the e to the minus t. Okay, so once you know what y equals, we also need to know what dy over dt equals. But I can do that just by differentiating. Notice that I'm still dealing with just that first equation. I haven't put it in just yet. So I've differentiated it. Dy over dt equals d squared x over dt squared, and so on, minus 2 dx over dt plus, so remember I'm differentiating this in terms of t, plus e to the minus t. Okay, right then, once we've got that part then, now what we can do is we can substitute both those parts back in. So we've got the y value, we've got the dy over dt, we can substitute both those back into here, and lo and behold, it will cancel out the y values. So there we go. Look, there's no y values in our equation. It might look a bit more messy. Bit of rearranging though might help us sort this part out. Remember that when you've got a second order differential equation, you want all the variables with x in over this side, and then anything that's left with t, they can stay on this side as a function. So I can rearrange it, just confirm you're happy with that, to that equation just there. So you've got the second order derivative there. We're going to add dx over dt. That's why there's only one of them. We've also got a minus 3x there and a plus 2x here, so that's going to go over the other side to make an x. E to the minus t can go over this side, but notice it cancels with that e to the minus t as well, all right? Because you're going to be taking that away, and this one's going to be positive. All right, so you end up with this equation. Right, once you're here, you can just solve this as you would do with any second order differential equation. So you can get your auxiliary equation, and then once you've got your auxiliary equation, there it is, we get your two solutions. Oh, interesting, it's a complex roots, so therefore we can write out the correct equation for it. X equals a half t a e to the root 3 over 2. Okay, right, once we've done that, then what we can do is we can actually solve it, which we've done here, and then once we manage to solve it, we can get the particular integral. So we've solved it to get the general solution there, and that's going to be what happens when it equals to 0. So then we can find the particular solution. So we're going to use this. Just double checking it's nothing the same as the others. No, it's not. It's a completely different type of function. So therefore we can just write it as a e to the 2x. Substitute back in. So we can differentiate it twice to get to that bit. So we're going to get 4a e to the 2x. This bit will be minus 2a to the x. And then you've got just plus a to 2x. Dum 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 dum. 4 take away 2 is 2, plus an extra 1 is 3. So 3a e to the x, so a must equal 2. So I've managed to calculate a particular integral and worked out what the a value is there. Now all I need to do to get the general solution of x in terms of t, I can just put these two together. So what do I end up with? the first solution there, which gets you 0 when you differentiate it and substitute it in, and differentiate it twice and substitute it in because you need it in both those parts, plus 2e to the 2x. Now that bit, when you differentiate it and when you differentiate it again, that's going to cancel down to make the 6e to the 2t. Okay, so I've managed to get my equation, what x equals. What I can do now is I can work out what my y value is then. And how can I get y value? Well, I can substitute it into either of the equations. It's up to you. Maybe thinking this one might be a bit easier. But I can substitute it in. And substitute it into this equation, but notice it's rearranged to make y because it's the equation I had earlier on. Doesn't matter if you just went straight back to that one, you'll get the same answer. So I've done that. I can certainly substitute that in for the dx over dt. So that's what I'm going to write. I can certainly just rearrange these parts and hopefully cancel some stuff down. So what do I get? A half e to the half t plus 4e to the 2 over t. Okay, so I'll just use that. Right, what next then? Well, I can simplify that and I end up with this equation, a plus root 3b, and so on. Okay, so we managed to factorise. It's worth just keeping it in that form because there's a good chance you might need to use it as a bartering tool. Okay, so I've got that. Once you know that, then what you can do is now you've got a general solution for y, you can substitute it in. So you can see I've substituted it in there for dx over dt, minus 2 lots of whatever your x value is, which we know is going to be 2e to 2ac, and then what? Then you've got minus 2 lots of x. Okay, so that's minus 2 lots of x, minus e to the minus t. So I've substituted in my x value and my dx over dt value. Right, why does that help us? Because then I should be left with just what y equals. So a bit of cancelling through, maybe a bit of expansion. So I can get this. But what I've noticed is when I actually expand it, we might have done a little jump there because I don't want to keep poisoning my ears. So once we get to this stage, that is it. We've got a general solution of y in terms of just t, and we've got our general solution of x in terms of just t. Okay? Right, so what I'd like you to do, please, is just have a go at the exercises on 12D on page 287, and you notice it's just the first 5 exercises, nothing more than that. Okay, so sticking with your notebooks, bit of writing, but you might want to just cut it down. What we're going to do is just show how you can go from a word example into a coupled differential equation. So in this situation then, just to pause and give you a chance to get done what you need. So just pause there. Okay, so what I'm going to do is we're going to find the differential equation, give you an opportunity to solve it yourselves. So in this case, the area is populated by a number of walls x and a number of hares y. So it's quite a simple model. It's called a predator-prey model. So the number of wolves increases at a rate of population to the number of hares. So you can imagine that the more hares, the more food around, so therefore more wolves. More wolves eat more hares, so the hares start to drop down, therefore the wolves start to drop down, and that's what you get. You get this sort of fluctuation of the populations going up and down. So the number of wolves increases at a rate proportional to the number of hares, and when there are 120 hares, the number of wolves is increasing at a rate of 15 wolves per unit of time. So that looks like I need to do some sorting out. I've got some sort of differential equation being produced here because I've got a rate, and some of the others may just be to get some constants. If there are no wolves present, the number of hares will increase at a rate of 120 in a unit period of time. When both wolves and hares are present, the wolves kill hares at a rate equal to 112% of the current number of wolves. Okay, so the more wolves, the higher that percentage. What I want to do is try getting rid of all these words and see if I can boil it down to an equation. Okay, so the first thing I'll do is just I'll go through each of the parts and see if I can work out what they're actually telling me. So let's take this first bit. The number of wolves increases at a rate proportional to the number of hares. So the rate proportional to. So because it's talking about rates, it's talking about change in x or y over time. So the number of wolves increases at a rate proportional to the number of hares. So we've got this sort of equation. The number of wolves changes at a rate, so that's the change in the number of wolves, the change in x over the change in time, and it's proportional to the number of hares. So it's proportional to y. So there's my first differential equation set up. Now let's look at this one. When there are 120 hares, the number of wolves increases at a rate of 15 wolves. So all they're doing there is they're giving you the value of dx over dt, and they're giving you a value for y. So I can both of those, I can substitute them in and get a k value of 1 over 8. Okay, so I've just managed to work out one of the differential equations. So I'll keep a note of that. So dx over dt is 1 over 8y. So that's the first bullet point sorted out. Right, what about the next one then? If there are no wolves present, the number of hares will increase at a rate of 120% in a unit period of time. So that's your t value. So I could write it like this. The change in the population of hares is equal to 1.2 times by the number of hares itself. Okay, so when there's no wolves present, the number of hares will increase at a rate of 120% in unit period of time. So that's what it's saying here. The change in the y value, change in the number of hares, and the change in time is equal to 1.2, 120% of the number of hares. Okay, that's it, you're done. But this one hasn't quite finished. Okay, because the rate of the population is not just based on the hares living on their own. We do have a situation where there's wolves and hares at the same time. So yes, they might increase at 1.2, right, if there's no wolves around, but you do need to take away the other part. And in this case, it's 1.12 of the current number of wolves. Okay, so the rate of population of the hares is 1.2 times by however many hares you have, take away 1.12 times by the number of wolves. So the wolves eat away at the hares. That's going to give you a second differential equation. Now, once you've got those two differential equations, you can now have a go at solving them. So you're now in a position to solve it and see if you can work out a formula for the number of wolves at a certain given time or the number of hares at a certain given time. Okay, this wants to construct a differential equation for the number of hares at a time t. So I need to rearrange it and get my y value. Okay, so you might be tempted to look at that top equation and go, oh, that's really easy to work with. I could just differentiate both sides and I could take a y value and substitute in there, and I could work out dy over dt and substitute it in there. And therefore I could easily calculate dx over dt. But don't forget what you're actually being asked to work out. We want to find a differential equation. We don't need to solve it. We just need a differential equation for the number of hares. That's your y value in terms t. So in other words, it's worth keeping these dy over dt's in here. And the only thing you've got to deal with is an x. Bit of a problem though, we don't have x. So how can we get around that then? Well, the first thing I'll do is, I know I haven't got an x, but I do have a dx over dt. So if I differentiate this bottom equation and get that x as dx over dt, okay, by doing that, then I can just do a substitution in, and then I'll be sorted. So I've got the second derivative there equals 1.1 dy over dt minus 1.12 dx over dt. And if I substitute that in then, I've got 1.12 times by an eighth y. So there we go. Can I neaten this up a little bit? Yes, you can. Second derivative times everything by 100. Might be able to make it a little bit easier. Yes, that's just neatening that bit up. But if I times through by 100 then, I should get a differential equation to do with the number of hares. And there we go. Got the y values throughout. So therefore I've got my differential equation for the number of hares. Okay, let's pause there then. Take any notes you want. Okay, so let's look at a second worded coupled differential equation question. Now, what I'm going to do is give you an opportunity just to write down what you need and maybe have a go drawing it out yourself. Okay, so I'm going to pause there, give you a chance to do what you need to do. Okay, So the first thing we want to do is we want to find the values of this unknown lambda here and the unknown mu value, which is there. Okay, now the way I'm going to do it is by first of all just sketching the situation, so I'll get an idea of what's actually going on here. It looks like I've got two tanks, two water tanks. So tank A holds 500 litres of water, or has 500 litres of water in it. So there's tank A. Tank B has 1,000 litres of water, so I can mark down both of those. There you go, tank B with its 1,000 litres of water. So there's my two tanks. I know in tank A there is water flowing into it. All right, and the amount of water that flows into it, salt water is pumped into tank A at lambda litres per hour. Okay, so I could show that by just drawing an arrow, and there we go, lambda litres per hour flowing into tank A. We've also got tank B, and we have 3.9 litres per hour. Notice I'm just dealing with the litres per hour. I'm not worrying about the concentration just now. Alright, so I'm ignoring the 3.3, I'm ignoring the 20. I'm just concentrating on what's actually flowing into these. Alright, so flowing into here is 3.9 litres per hour. So there we go. 3.9 litres is flowing into tank B. What else do I know? There's two connecting pipes, one from tank A to tank B, and that's flowing 10 litres just there. Alright, so a certain amount comes in, 10 litres definitely flows out there. Notice that we've got 13.9 flowing into B, just for these two. Alright, the bit from A and the bit outside. But we're going to lose a bit because there's a bit that goes from B to A, and that is 4 litres per hour. So there we go. So I've got my 4 litres per hour flowing from B to A. Alright, so I've managed to put all my litres on. And what I've noticed, is also water is released in tank B at a constant rate of mu litres per hour, so the amount of water in each tank remains constant. Because if you look at tank B, for example, we can see that 10 flows in here, 3.9 flows in here, so 13.9 are flowing into it, but 4 litres is flowing out. Now, if it's going to remain constant, right, these are all supposed to be equal to each other. It's a bit of a flows question. So water is released in tank B at a constant rate mu. So I think we're in a position now to start thinking, what is our mu value of litres per hour and what is our lambda value? So if I look at my lambda value, I know that 4 flows in there, lambda flows in there, but 10 flows out. So the only logical answer for lambda in this case, is that lambda plus the 4 must equal the 10 flowing out. So what does that mean then? Well, I would say that lambda equals 6 litres per hour. Okay, what about tank B? Well, tank B has 3.9 and 10 flowing into it, but 4 and mu are flowing out. So what does that tell you? That mu must equal 9.9 litres per hour. Okay, so I've just used the lambda values and the mu value. So I've calculated my lambda value and my mu value, and all I'm using there is the number of litres. I haven't done the concentration yet. That's coming up next. Right, it's part B. Show that the system can be modelled using coupled differential equations. So I need to show coupled differential equations on this one. So before I can do that, I need to look at the concentration of salt at time t hours on the diagram. So I need to put the concentration of salt now, right? What's flowing into the things, what is in the things, all those types of ideas. So I know that this 6 litres here, this 6 litres that's flowing down here per hour is got a concentration of 3.3 grams of salt per litre. So what I can do is I can put that on because I know what was flowing in. It was 6 and it's 6 lots of 3.3 grams of salt per litre. So I know the concentration there is going to be 19.8. Okay, so 6 lots of 3.3. What else do I know? Fresh water is pumped into B. So it doesn't matter that it's 3.9, its concentration is going to be 0. There's no salt in it at all. That's fresh water flowing in there. That's salt water flowing into that one. Right, what else? Well, once I know that, I know that there's X grams of salt in tank A. So I've just got X grams of salt here. It's X grams of salt out of 500 okay, out of 500 total. So it's x over 500 per litre, okay. So it's only maybe a few grams of salt divided by how many of litres of water you've got. And the same idea for part B, okay, but don't forget this time there's 1,000 in there. So I've got this changed to y out of 1,000 per litre. Right, so there we go. I've set up my x's and y's. I've set up the concentration of what's flowing into it. I think I could probably do something with these two. So I know that I've got x over 500 here, and that's going to be flowing into tank B. It doesn't matter what tank B's concentration is like. I just know about what this concentration is, and there's 10 lots of it going in there. So I would say that is 10 lots of x over 500. Whereas this one is this one flowing out, 4 lots of it. So I would say that is 4 lots of y over 1,000. Okay. What else? Oh, I haven't done this bit. What's venting out? So that bit there is going to be 9.9 lots of y. So it's 9.9 y over 1,000. So I've gone through and I've just converted everything to the amount of salt. Okay, either in terms of x or y, depending on which tank it is. Right, so I've put the concentration of salt on my diagram. So what I can do now is I can replace all that writing and just keep my diagram up there to help me with the rest of the questions. Right, so I'm going to use a diagram with all the information. So the amount of salt in tank A is the amount of salt flowing in minus the amount of salt flowing over the time t. So let's just get a head around this again. So the amount of salt in tank A is the amount of salt flowing into it minus the amount of salt flowing out of it over any given time, t hours. So that's what the salt's going to be. So I know that my change in my salt in tank A, so that's the change in x, so that's the number of that's the concentration of A. So the change in x over change in time is equal to, well, 19.8 flows in. 4y plus 4y over 1,000 definitely flows in, but I'm losing 10x over 500, which is where that part comes in. Perfect. What about for part B? Well, here's the second tank. We know that's got y per a litre in that tank. What could I do with this? Well, I could take that and I could differentiate first to get dy over dx. And then once I've got that part, I can see what is the change in the amount of salt in tank B, because it's a change in the y value, the change in the concentration of y over time equals what flows into it, or 10x over 500 does. What flows out of it, oh, I can ignore the 0 because that's not going to change the concentration at all. So what flows in is 10x over 500, but what flows out is 4y over 1,000 and 9.9y over 1,000. Now, yes, I can combine those two together, and I do. So I get this 13.9 y over 1,000. So I've got my two coupled differential equations set up, and I could potentially pause there and ask you to work out the next few questions. Okay, so we have a look at part C. It says solve the differential equations and find x and y in terms of t. Okay, again, it doesn't really matter which one you pick. Okay, so we've managed to get the equations out of all those worded examples and that real life situation, and now we're expecting to actually solve this using our techniques of solving coupled differential equations. And this is worth pointing out, the same with a lot of these questions, if they give you a worded one, it's highly likely they give you the equations so you don't get penalised for not being able to do the solution part as well. Okay, so what you need to be doing is you need to pick in any equation, doesn't matter which one you pick, and we need to figure out what either x and dx over dt are, or y and dy over dt. It doesn't matter which one we pick. So I'm picking this equation just here, so I've wrote that one out. And then what I'm going to do is I'm going to work out both the x value, what x equals, and what dx over dt equals. So I know that x equals this, but also dx over dt, if I just differentiate everything in terms of t, so I've got 50 dots of that, I've got this in terms of dy over dt, then I've got an x equation, I've got dx over dt. There is nothing wrong with you guys getting y and dy over dt, that's perfectly reasonable, and there's nothing wrong with using that equation first. Okay, they all lead to the same result. Once I've got this result, I can now substitute both of these into the second equation. All right, so I'm going to get my into the first equation. So I've got my dx over dt equals 19 plus da, 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 da. I'm going to substitute the x into there, and I'm going to substitute dx over dt into there, and end up with this equation like this. See, I've just got that for the dx over dt, and 0.2, which is the 10 over 500, lots of my x value. So there we go. I'm substituting both in. I think you can neaten this up a little bit. We can expand this. Fifth lots of 0.2, 0.2 times that. So there we go. Just neaten that bit up a little bit. I could rearrange. So I could maybe take everything to one side. Maybe not the 19.8. And there we go. I've got that equation just there. And now we've got a standard second order derivative that you can go and solve. All right, so we can solve that equation. So what I'm going to do first is just write out the auxiliary equation. All right, so the auxiliary equation looks like that. It's my quadratic. It looks messy, but it is based on a real life problem, so it's expected to be a little bit messy. So once I've managed to get this, I can then find my two roots. They're both, it's get real roots, that's good. So I've got my two roots, so I can get my complementary function and by substituting both of those in. So there we go, y equals a to the minus plus b equals e to the minus t. So I'll substitute both those in. And now I need to deal with the 19.8. 19.8 is very easy to find a solution. You could just set y equals 19.8. Because when you differentiate, it goes to 0. When you differentiate a second time, it goes to 0. So therefore, we can just get 19.8. Alright, be careful though. Obviously, if y equals 19.8, then you've got 0.009 times it. Alright, so in this case, what times y is going to equal 19.8? Y equaling 2000. If y equals 2000, then 0.0099 times 2000 is your 19.8. And that's it. I've got my general solution then. So I've got that, and I've got that, and I can just combine those two together, those two y equations, to get this. Okay, so well done if you managed to solve the coupled differential equation and then understood how to solve the actual differential equation itself. We're not quite finished just yet. Okay, we can differentiate it. We still need to find the x. So we could differentiate it and get your dy over dt. And why that's going to help is now I can substitute both of those in to get the x in terms of t. So I can do it the other way around. So I can get my x equals 50 lots of dy over dt equals that. So I can see I'm just using the previous equation, which was that one rearranged. Once I've got that, I can substitute those in. So substitute that in. There we go. Substitute the y value back in. There we go. And so what I can do now is I can just simplify and solve it. So there we go. I've simplified it, solved it there, and I've got my x equation sorted there. So I've got both my a and my x in terms of t and my y in terms of t. Okay, quite a big question. You get loads of marks in the exam for it, and they're more likely to hold your hand through certain steps. Okay, but we haven't quite finished because we've got the general solutions, but we can get the particular solutions. So it gives you the initial conditions. When t equals 0, there's this much for x and this much for y. So I told you the concentration of each of the tanks. And of course, you can make use of those by substituting them both in. So you can substitute when x equals 38.2, y equals 0, and get you that equation. But also, with a bit of rearranging, also the other equation, 20 equals a plus b plus 2000. There we go. So that's going to get me a plus b equals minus 1980. So I've got my two equations, solve them simultaneously to get your a value and your b value. And it's very well done. So the concentration of salt in each of the tanks at any given time is x equals this number here. There we go, with my a and v value subbed in. And this one is going to be both of those values for a and b. And there we go. So I've got my y equation. So you can manage to work out. Someone said to you, what's what's the concentration of salt in both tanks at a given time. You can stick the 2 value in there and you can work out what the salt is for X and what the salt is for Y. That's what those equations do. Okay, just pause there if you need some more time to take notes. Okay, so what I'd like you to do is just finish off that exercise. You started it a little while ago. Now you can have a go at finishing it with some more worded type problems on 6 to 8.